which the top one is being reduced or does turn into initial based on the perspective that it is reducing to its initial value. Then once you try to do this, you're going to have negative kt is equal to the in. What is happening inside are going to have initial concentration divided by 2. Then the division of initial concentration, just step by step, is equal to negative kt, which is constant at time there, is equal to the in. What is happening inside there, you're going to have initial concentration divided by 2. Multiplication, or to say, once this division turns into multiplication, then everything gets affected, whereby 1 goes up, then the initial concentration of the first reactant, as in original, remains one and the same. Then I'm going to have that constant there and time is equal to in, which is natural log. Then what I'm going to have here is initial concentration there times 1, that is initial concentration times 2, that is initial concentration there. Then this one goes, and therefore going to have negative kt is equal to the in of 1 over 2. And in this case, if you see very much properly, can we try to affect the appearance of negative? Shall we? Let's go. So negatives are negative, that is kt is equal to, what is the in? Negative in of 1 over 2. This is same applies, kt is equal to log 2, which is over k, and our answer still remains the same, which is 1 over 2 is equal to 0.693 over k. So this is our formula for half-life of the first order of the reaction. So what I'm trying to do is this. If you try to punch negative log, which is the in, natural log, open up 1 over 2. What are going to have? We're going to have 0.693. So for instance, again, if we say the in, there are some of the questions that you're asking yourself, of 2. What is it? Is 0.693, which is one and the same. Okay, what about the last one? Go in the second order of the reaction with the same formula. So if you see very much properly, the formula has been, let me say, a little bit tempted. Yeah, but that is not our main focus. Our main focus is delivering the formula, half-life formula for our second order of the reaction. I'm going to deliver it. Shall we? Let's go. If you see very much properly, we have 1 over, we're not to say half-life, talk about the decrease, or let me say the time taken of which the concentration of the reactant decreased by the half of initial value, So what's going to happen, I'm going to have initial concentration there is equal to kt plus 1 over, which is initial concentration. What I'm going to do, it has already affected whereby 1 over something, so which means it should be a quarter, So what I'm going to do, we're going just to multiply by 2, which means the upper part, and in this case, this turns into 2 over initial concentration is equal to kt plus 1 over initial concentration, of which if you try to rearrange them, we're going to have 1 over initial concentration plus kt plus 1 over initial concentration is equal to 2 over initial concentration. Okay? Step by step, that's the second order of the reaction. So shall we correct the right terms? It is kt is equal to 2 over initial concentration minus 1 over initial concentration. Should we find the common factor there? A common denominator going to have initial concentration itself, of which they are going to have 2 minus 1. Understand it clearly. We are down here going to have Kt is equal to 1 over initial concentration. Now looking for T, time taken, divide by K. So this K gone, and we're going to have time taken, of which the concentration of the reactant decrease by half, which is equal to 1 over the initial concentration times 1 over K, which is equal to, therefore, the time taken 1 over the net constants of the initial concentration of the first reactant. So this is the formula of what? Second order or the reaction half-life. Okay? We have what we call reaction mechanism. What is it? Just a series of what steps? What are these steps? Elementary step to come up with a original equation out of different equation. Can be a 4 or 3, 5 equation. So what's going to happen again in this reaction mechanism? We are made up of, or we do have what we call intermediate compound, where also they do participate in both reactant and product, but they do not exist, or they are not in the exact, which is the original equation. Not only that, we have got also some collision that do happen in reaction mechanism. That's what we call molecularity. So the molecularities are one of the properties that describe the unit molecule and also biomolecule and term molecule of reaction mechanism. So what do we mean if we say that? So this is our original reaction. I'm just touching a little bit, not in detail, about reaction mechanism. So what I'm going to do here, if you see very much property, I've got nitrate dioxide also appearing for this reaction, and also I've got carbon monoxide, and also I've got nitrate monoxide and also carbon dioxide. So all in this equation, what is the intermediate compound? It is nitrate trioxide. That clearly, let me say nitrogen trioxide, that clearly indicates to say this reaction do not supposed to be in here. It is an intermediate. It's just one of the predisposing, just one of the stimulator to say the reaction is producing such kind of product. And in actual sense, it is not appearing in the exact equation after filtration has taken place of the reactions, just to say, or just to make a clarity on that purpose. So I've got also nitrate trioxide in this case. If you see very much proper, I've got only the first reaction, which is before the coming in of the original reaction. I've got only one compound which is intermediate, and in this case it is nitrate or nitrogen trioxide. Now, should we come up with the exact equation? And the exact equation should be like reaction mechanism, which is original on top. That is nitrogen di plus nitrogen di plus nitrogen tri plus carbon mono producing tri plus nitrogen mono plus carbon dioxide, and also nitrogen di. So if you see, di gone with di, nitrogen dioxide going with nitrogen dioxide, we have nitrogen trioxide and also goes with nitrogen trioxide. The other going to remain with, it is nitrogen dioxide plus carbon monoxide producing nitrogen monoxide plus carbon dioxide. And this clear is setting to say we have the exact equation on top there. Yeah. Now, like what I said, the corrosion in chemical mechanism, that's what we call molecularity, which is one of the properties which describe either it is unimolecularity. What do you mean if you say unimolecularity? So the unimolecularity or molecular, that means to say we're going to have one product here, one reactant producing just direct product, and not to say always the product or always the reactant do decrease, the product do increase. So what's going to happen once we have such, we're not to say lighting, the differential lateral, we're going to have rate constant and also the concentration which depend on what? Reactant. And in this case, what is the order of the reaction? It is only one because we're only having product and it's having been described in the manner such that we do not have any compound. So it remains one like that. Now, we talked about also by. So that means to say you might have two different reactants producing a certain product. That means to say we're going to have rate is equal to constant, and also we maintain the product like that. Not only that, we've got also what we call molecularity or molecular. So where we're going to have two different or three different what? Three different reactants. Where we're going to have rate is equal to constant just like that. What about in the sense where we have three same reactant producing a certain product? Just try to assume kind of question. Hence, what would be our final answer in terms of differential lateral? We want to say differential lateral depend on the concentration of the reactant. So hence we're going to have constant